Hello, welcome to our second chemical equilibrium video. In this video, I'll be telling us about equilibrium constants. Now assume we are given a reaction like this, A and B combining to give C and D. The M, N, P and Q there are described as the coefficients of A, B, C and D respectively. Now for such reactions, it is true that when we take the concentrations of the products and raise them to the power of their coefficients and then divide that by the products of the concentrations of the reactants raised to the power of their coefficients, what we get as result is usually a constant. That is as described as two people. We call them Cato, Goldberg, and Peter Wage. And that law or that principle is described as the law of mass action. The law of mass action. Some others call it the law of Goldberg and Wage. So the law of Goldberg and Wage is the law of mass action, and that law is as shown here. Here is Kc. Kc means equilibrium constant in terms of concentration. And the expression here is showing us that Kc, a constant now, is equal to the concentrations of the products, which are C and D, raised to the power of their coefficients, divided by the concentrations of the reactants, multiplied together now, raised to the power of their coefficients. So this expression we are looking at, we call it the equilibrium constant expression, Kc expression, or mass action expression, because that expression is written according to the law of mass action. So the law of mass action is what we are seeing in an expression here. So that's how we write the Kc of a reaction. You take the products, and if they have any coefficients, raise them there as powers, and the reactants should do the same. Now, apart from Kc, it is also possible to talk about Kp. There are many equilibrium constant types, as a matter of fact. But for this video, we'll just assume that we have Kp and Kc as the two types of equilibrium constant. Now, the difference is, while Kc focuses on the concentrations of the species involved, cases where we have gases, it is easier to measure Kp than to measure Kc. Why? Because it is easier to talk about the partial pressure of a gas than to talk about the concentration of a gas. So concentration is more appropriate when we deal with aqueous solutions, but when we deal with gases, it's more appropriate to talk about the vapor pressure. So for Kp expression, it deals with vapor pressure, partial pressure now, whereas C, concentration, so Kc deals with concentration. So how do we write the Kp expression now? We've talked about Kc. For Kp expressions, you have two ways of writing them. To avoid controversy, you could write your Kp this way. So Kp becomes partial pressure of C raised to power P, then partial pressure of D raised to power Q, partial pressure of A raised to power M, and then partial pressure of B raised to power N, like we already saw. So the difference between these two is, while we were saying concentration there, here we're saying partial pressure, which is the P you have there. But it is not every time we write Kp expressions and you see the P. Some other times we use brackets like this. Now these brackets are different from those ones. Those are square brackets, and these are round brackets. So these round brackets are used to denote partial pressure. So if you ask me to read what is there, I'll say concentration of C, concentration of D, but here I'll say partial pressure of C, partial pressure of D. So these are Kc and Kp expressions. Now, for some reactions, we calculate the Kc from the given information. For some others, we calculate Kp from the given information. But there are times when you are given one of them and asked to calculate the other. In that case, you would end up getting your Kp from Kc or Kc from Kp, as the case may be. I'll show you the relationship linking the two. I'll show you an equation linking the two of them so that you can see how to calculate your Kp from your Kc and vice versa. But for now, there's a simple question here. It says, given that the equilibrium concentrations of A, B, C, and D, that is in this reaction, so you're going to allow me remove the M, remove the N and put 2, remove P, remove Q and put 2, or let's put 3 here in any case. So we have altered those values a bit. Imagine that you were given the reaction like this. So it means I no longer have P, Q, M, and N. I have real numbers there now. So here's the question. It says, given that the equilibrium concentrations of the 4 of them, A, B, C, D, are 1, 2, 3, and 4 moles per dm cube respectively, calculate the value of Kc. That will be a very easy question in that to calculate Kc, I'll use this expression. Just that in place of P now, I'm going to put what there? 1. In place of Q, I have 2. In place of M, I have 1. And in place of N, I have 3. So this becomes the new Kc expression since I have introduced coefficients. So bringing in the values supplied, Kc will be equal to, what's my C? My C is 3. So let's just write 3 there. Then on the other side, I have 4 raised to power 2 over A is 1. And then finally, B is 2. But that 2 would now be raised to the power of 3. So my Kc here becomes 3 times 4 by 4 is 16 over 1 times 2 raised to power 3 is 8. So this Kc becomes 3 by 2 and that is 6. So I have the Kc of this reaction at 6. And the value should usually be expressed at a temperature. So this question should have given me a temperature. Maybe it says calculate the value of Kc at 20 degrees Celsius, given that the equilibrium concentrations of these things are as shown at 20 degrees Celsius. So in that case, I would have written my answer as Kc equals 6 at 20 degrees Celsius. But in any case, the most important thing is that you know how I am able to pick these values and put them into the expression. And then more importantly, that you know how I wrote this expression based on what we've said earlier in this video. Now, what if for this case, I am asked to calculate Kp? I've been given Kc already and they say calculate the Kp for this very reaction. How do I go about it? In that case, I would calculate Kp from the Kc using a relationship that I'm going to give to you now. If you need to pause the video, pause, because I may remove these things. All I'll need is the value of the Kc to proceed. Okay, I'll grab my calculator. Now here's the relationship between connecting Kc and Kp. There's a simple equation connecting them. It says Kp equals Kc RT raised to the power delta Ng. That expression is very important. It says Kc, or Kp rather, equals Kp RT delta Ng. Now Kp stands for equilibrium constant in terms of partial pressure. Alright, sorry, I don't have enough space for that. Then Kc, of course, is equilibrium constant in terms of concentration. But more importantly, R. R is the gas constant. Now, this is where you'd need to listen. In some calculations, we use our R as 0.0821. That's, we use this value for R in some calculations. But in some other ones, we use 8.314 for our R. So when do we use this for R and when do we use that for R? The value of R as 0.0821, we use that when pressure, so this value is used when pressure is in pascals and volume is in meter cube, or pressure is in kilopascals and volume is in liters. So which means you have pascals and meter cube or kilopascals and liters. When you have that, please, you use this value. I beg your pardon. So this value is used when we have these units for pressure and volume. Whereas the first value is what we use when pressure is in atmospheres and volume is in liters. So pressure in atmospheres, volume in liters, we use this one. It means that for this calculation I'm about to do now, if I put R as 0.0821, the pressure I'll be getting here, the Kp I'll be getting here, will be in what value now? Yeah, it will be in the value of atmospheres. But if I put my R as 8.314 here, then the pressure I'll be getting would be in kilopascals. So my Kp would reflect kilopascals. Usually it's kilopascals. Alright, so take note please, those are two values for R's. Then finally, the T, not finally anyway, because there's delta Ng to talk about there. The T is temperature in Kelvin. So if you are given temperature in degrees Celsius, you would need to convert it to Kelvin before you can work. Then the delta Ng there, what does it stand for? What's the meaning of delta Ng? I'll tell you. Delta Ng in that reaction stands for change in number of moles of gas. So look at it, change in number of moles of gas. So for this reaction, everything is gas. So because everything I have there is gas, I would say number of moles of gas, the difference now becomes number of moles of gas on the right minus number of moles of gas on the left. In this case, we have number of moles of gas on the right. This is 1 mole of gas. That's 2 moles of gas. So the total there is 3 minus the number of moles of gas here, 1 plus 3, and that's 4. So that gives me minus 1. So that delta Ng for this very reaction is minus 1. What if we had a reaction like N2O4 to give 2NO2, gas and gas? What would be our delta Ng? Yeah, this is 2 moles and that's 1 mole. So delta Ng will be 2 minus 1 and that is 1. Then finally, what if we had a reaction like CO2 plus H2 to give CO plus H2O? All gas, everything here is gas. In this case, it means 1 mole, so 2 moles of gas. On that side, we also have 2 moles of gas. It means therefore that delta Ng in this case will be equal to 0. Now see why this is a special case. A case where you have delta Ng equals 0 is very special, and I'll show you why from here. If delta Ng is 0, it means RT raised to power delta Ng becomes RT raised to power 0. And of course, anything raised to power 0 is 1. So it will mean that Kp becomes Kc times 1. In other words, Kp and Kc become equal. So any reaction where delta Ng is 0, that is, you have equal number of moles of gas on left and right sides, is a reaction where Kp will be equal to Kc. So at this point, without wasting time, I want to calculate Kp for this reaction, the same reaction. I don't want to bring in a different reaction. There's a reaction on the board already. Let's just use it to calculate our Kp. So we already got the Kc of that reaction. We got Kc as 6. And I would like us to assume that the reaction occurs at room temperature. We were not given in the question, but want to assume we were given for completeness, so that when you see a question that's different from this one, you can follow the same pattern. So here's my Kc, here's my T. For the R, I'd want to use 8.314. So that already means that the Kp I'll get would be in kilopascals, but most times you are not bothered during exams. Yes, the university will not bother you with the value. So that the next thing I'll be looking for is my delta Ng. Delta Ng now is 3 minus 4, and that is minus 1. We saw that before. So that finally I would say Kp equals Kc 6 into R 8.314 times the temperature. I won't use 25 degrees Celsius. Instead I'll use 298 Kelvin, then raised to power minus 1. So my Kp will be equal to, I'd look for that. Remember that that value raised to power minus 1 there is the inverse. So that would be the inverse of 8.314 times 298. So that gives me 6 times 0.00040. So my Kp would be equal to 0.0024 kilopascals. Alright, so kilopascals, I could write kilopascals per, what's the volume unit now? Liter. Kilopascals per liter, or kilopascals liter. So I'll just leave it at kilopascals. So this is my Kp. So Kp can be calculated from Kc very easily. What if this reaction were coincidentally like this? In that case, I wouldn't have solved at all. I would simply have said that Kp is equal to 6. Why? Because the number of moles of gas on the right would have been 3, then the left would also have been 3. And once they are equal like that, we said Kc will be equal to Kp. So sometimes you are given a set of reactions and they say, for which of the following reactions is Kc equal to Kp? Then it will be the reaction that has equal amounts of gas on both sides. So we're done solving Kp from Kc, and I expect that if you are given a question where Kp is supplied and Kc is to be calculated, you will know how to do change of subject or formula. So I'll remove this now. You can pause to look at it again. Otherwise, I'll remove it to talk about the equilibrium constants on that side, so that by the next video, which will be the last chemical equilibrium video, I'll show some calculations on chemical equilibrium. So see what we have now. Here it says A plus B to give C plus D, then C plus D to give A plus B. If we look at those two reactions, what's the relationship between them? You see that this one is the reverse of that, or you say that is the reverse of this. When two reactions are related like that, as in they are the reverse of each other, then if the Kc of the first reaction is, let's say, 4, and you are asked to calculate the Kc of this second reaction, just know that it will be the inverse. By inverse, I mean 1 over 4. So 1 over 4, 1 divided 4, which is the inverse of 4, will be the Kc of a reaction that is the reverse of a reaction whose Kc is 4. So if you reverse a reaction, you invert the Kc. The reaction we put here before was ABCD as well. If the forward reaction has Kc of 10, then the backward reaction will have Kc of 1 over 10. So it's always like that. Forward and backward, their Kc's are the inverse of each other. Now, having said that one, look at this second case. If you ask me the relationship between these two guys, I would simply say that equation 1 has been multiplied by 2. No wonder 1a has become 2a, half b has become 1b, and c has become 2c. Now, when you multiply a reaction, assuming this case here is 2, when you multiply a reaction by a factor to get a new reaction, then you are going to take the Kc of that reaction, which is 2, and raise it to a power. What power? The power that's equivalent to that number you multiplied by, which is 2 raised to power 2. In other words, if I had multiplied this first reaction by 4 to get the second reaction, then I'll raise the Kc of the first reaction to power 4. If I had multiplied the first reaction by 20, I would have raised the Kc here by 20. So when you multiply a reaction by a factor, you raise its Kc by that same value. Then finally, look at these 3 reactions. For these 3 reactions, if you observe closely, you see that if you add up these 2, you are going to get the third. How? Let's add them up. Whenever you want to add reactions, you add everything on reactant sides, then add everything on product sides. So it means I'm going to get A plus B plus C plus D to give C plus E. So I've added both reactant sides and both product sides. Now based on that, there's C on both sides, so I'll eliminate it, and that leaves me with A plus B plus D to give E. Is that what we have down there? Yes. So anytime you add up 2 reactions to get a third one, you will take the Kc of the first and take the Kc of the second, and you multiply them so that K3 here, which is the Kc of this third reaction, will be equal to K1 times K2. So if you add 2 reactions to get a third, multiply their Kc values to get the Kc of the third reaction. These are some rules telling you how equilibrium constants of different reactions are related. After the break, I'll show you in the third video how to calculate Kc for certain reactions, special cases, the ones where the reaction begins and then you want to determine the equilibrium concentrations of the products at equilibrium. So I'll see us after the break. That's in the third video.